Let's quickly look into boost converter. So this is your PWM. Let me draw the switch. Okay, true. V out is always less than 1, or in the best case is maybe equal to V in. So what can I achieve V out greater than V in? Okay. Can I write like this? Same thing, huh? Now, can I do this? Which means V in or VDD let me use the same VDD. So this is your VDD and this becomes my output. So if this becomes my output, I will need a capacitor also. So I will just put a cap here. C out. Okay. So what is the ratio now? V out is VDD over D, correct? So if I increase D, what would happen to V out? So V out is inversely proportional to D, but I want output to increase when duty cycle is increasing, correct? So to get this, instead of I will do this, which means I will make the relationship V out equal to 1 minus D times, sorry, VDD over 1 minus D. So D is replaced with 1 minus D, which means your high side switch will be, and what is the, I mean high side switch is basically, which is the, I mean which switch is charging the inductor, think that way, the bottom switch or top switch? Which switch is charging the inductor? Bottom, huh? So which means your PWM will, duty cycle will drive the bottom switch, not the top switch. That's why it becomes 1 minus D. Okay. So now I will flip the whole converter and draw this way. This will D, this will be 1 minus D. This is VDD, this is your V out. So this is like a intuitive way of looking into that, but if I want to derive that equation, that whether it is true or not, how do we do that? You guys remember volt second balance? Okay. So in one cycle, average current, average voltage across the inductor should be 0. So during on time, what is the voltage? So on time is this VDD into T on, okay, and during off time, this is your volt second, volt second, okay. During off time, your volt second is how much? What is the voltage across the inductor? VDD minus V out into T off. So the average is how much? VDD into T on plus into T off. Okay, if you want to write in terms of average, you have to simply divide it by TSW. Okay, but that becomes 0, so you don't need to. That's why we call it volt second. Volt second is not a average voltage actually, it is a product of, but ultimately it comes from here only. So since right side is 0, so as good as same. So whether you say voltage, average voltage is 0 or volt second is 0, it's same thing. So now VDD into T on is, you can write T, let's write in terms of duty cycle. So your VDD D times TSW, okay, plus VDD minus V out 1 minus D TSW equal to 0. Which means D times VDD equal to how much? V out 1 minus D minus 1 minus D into VDD. Correct? D times VDD equal to V out into 1 minus D minus VDD plus D times VDD. So this is gone. So V out equal to VDD over 1 minus D. Okay. So that was the intuitive way, but if you don't know, then you can always drive. And this is true for any switcher actually. Even if you have a, let's say I put one more switch pair of switch at input side, output side, then you can still derive the same equation. So when we talk about the buck boost, then you have 4 switches there actually. So in the buck, I mean this is your buck, left side is your buck if this is connected to input, right side is your output, and if you have a switch at the output side, then it becomes boost. Now you have a switch on both the sides and you operate only 2 switches at a time depending upon whether you want to configure in a buck or boost mode, and that becomes a buck boost actually, 4 switch. So we will talk about that later. So for ideal converter, P out equal to P in, which means V out into I out equal to VDD into IDD. And V out we already know. What is V out? VDD over 1 minus D into I out equal to VDD into IDD. So, what is IDD here? Which means your current is also boosted, the current which is drawn from the supply. So, let us say I am operating at 50% duty cycle, my input is 2.5 volt, what should be the output? 5 volt, 2x, and what should be the, and it is the current is 1 amp, then the current drawn from input is 2 amp now. Okay, so if you operate at very high duty cycle, let us say operating at 90% duty cycle, you are looking at 10x current drawn from the input. So, and if your current is more in this inductor, what would happen? Which loss will increase? Magnetic. I square R loss, 2x current means 4x more loss. If it goes from 1 to 2 amp, if you have, let us say all the conditions remain same, you are looking at 4x more losses. That is why boost, actually you cannot arbitrarily operate at any high load current. So, whenever we design a boost, we usually do not do for very high current. The load may be limited to 1 amp or less than that, boost converters, especially if your voltage to input ratio is high. If you are looking 4x, 5x boost kind of thing, then you cannot just say that I can build a 1 amp current and get a 10 volt output from 2 volt. It is not that simple. You have to look for then very small DCR inductor and very small RDS on. Okay. Okay, any questions? Sorry? No, you can do that, but again the efficiency problem would be there. You can cascade to boost, okay, and the moment you cascade, so let us say you are getting a 90% efficiency from each, you will left with how much? 0.9 into 0.9, 80% efficiency, 10% is lost. So, the same you can achieve by single stage and say one inductor, one inductor and 2 switches. So, ultimately it will not benefit that much when you do in stages. You do in stages, we are limited by duty cycle. So, let us say I limit my duty cycle to 10% and I want 20x. So, that is not possible. So, in that case you do 2x and 10x or 5x into 4x, you get 20x. Okay, so I will not go in detail about the controller and everything. So, but I will just briefly tell you there is one problem with this boost, that it has a right half plane 0, just like you had in LDO. Okay. So, what does right half plane 0 do? Gain is increased and phase is, so phase response looks like pole and gain remains same as 0. So, it makes it even worse actually. So, which means your output does not change in a fashion what you want. So, if you guys remember the in case of LDO, when you had a right half plane 0 or wherever you have a right half plane 0, let us say my inverter has a right half plane 0. So when you give an input clock, what do you expect at the output?
For some time it will follow the input only.
It will follow the input, correct? And then after that it will change. So which means, so I expect this, but what will happen? You will see these glitches, and you can see in the simulation, and this is nothing because of your this cap. So the same thing will happen here also. So I am trying to change the duty cycle, increase the duty cycle. What do I expect? My output to increase or decrease? No, that's what I expect. But in this case, it will increase or decrease.
Depending on the overshoot and undershoot, the average voltage will change.
For, forget about undershoot, overshoot is transient thing. Huh? I am simply changing the duty cycle to change the output. I am not even looking at the load transient or anything here. I want to just change the output. Let's say I am operating at 5 volt. Now I want to bring it to 10 volt by simply changing the reference voltage. Let's say. So my output should follow the step. Okay, let's say my reference was 0.6 volt. At 0.6 volt, my output was 5 volt. Now I make 1.2 volt reference. I should expect a 2x output, which is 10 volt. So I simply give the step, it should follow the step, but it will look like something what you are seeing in the inverter, because it has a right half plane 0. But intuitively, if you want to explain, how will you? So where is the charging switch? With the ground or with the output? So when your switch is connected to ground, what happens to the output? Who is supplying current to the load? Capacitor is supplying, because it is disconnected. So there is a discontinuity between these two switches, between output and your input. So if I increase the duty cycle, which switch is connected for longer time? Ground, which means you are leaving your output disconnected for even longer time. So output should increase or decrease? It will start decreasing. But at the same time, your inductor current is rising. So next time when you connect the switch, inductor will supply all of a sudden huge current and your output will start recovering. Okay. It's like a bucket. Let's say you have a bucket and you are trying to fill it, that bucket, from a tap. Okay, and that bucket also has a tap which is leaking the water. So if you fill the bucket from the tap for a longer, your refill basically for a longer time, so that bucket will keep emptying, but then all of a sudden your bucket is full and dump into that, so that bucket will be full again. So it's some similar to that actually. So your inductor is basically keep on charging during on time, but at the same time your output is getting discharged through load. So if I want to improve this, how can I do? So this has a right half plane 0. Let me just, I mean intuitively I explained you what will improve the, so right half plane 0 due to discontinuity. So let's say I'll call it SN SP. inductor is charging but V out is discharging, causes so I'll just so omega z appears at 1 minus d square R out or R load over L. And it's obvious, why 1 minus d? Because this 0 will become dominant at higher duty cycle, and which means your omega g is coming at lower frequency. I mean, it will come at origin at 100% duty cycle, and you want to push this 0 at very high frequency. So, which means you operate at a very low duty cycle, then it may not be a problem, or you operate at very high load. High load means R load is large, means light, basically in other way, light load current. Okay. So, if I make this R load infinite, then it will be pushed at very high frequency, or you make in, what about the L? If I reduce the L, omega z will go high. Okay, so these are the ways to control this, and this will limit your bandwidth actually. So, I mean, for the D, R load and L values you have chosen, if omega z lies within your UGB, then it is very hard to compensate. So, the only way is to reduce the bandwidth so that it is pushed outside your, and sometimes this limits your bandwidth of your boost. So, if I want to take an example, let us say L equal to 1 microhenry, R load equal to 5 ohm, let us say I am talking about 5 volt. So, and D equal to 0.5, which means VDD equal to 2.5, V out equal to 5 volt. Okay. So, let us just do a quick calculation. Where is this? So, omega z will appear at 0.5 square 5 by 1 micro Henry. So, how much is this? 1.25 mega radian per second. So, F is 1.25 over 2 pi. How much is that? 6.28. 1.25 divided by 6.28. 0.2. So, 200 kilohertz. So, now I am operating at 1 megahertz. I want to keep at 100 kilohertz, 1/10. So, 200 kilohertz, this 0 is appearing. It will basically cause a significant drop in the phase margin. Now, assume your L is increased or duty cycle is changed, so that this omega z, this Fz becomes 100 kilohertz. So, it will right away make your phase margin how much? Minus 45 degree, that will be the whatever. If you have a 60 degrees, then it will, and it will reshape your frequency curve also. So, your omega UGB ultimately it will push at higher because gain will increase, so it will make it even worse. Correct? And I cannot cancel it. If I place a pole, that will again drop the phase and make my phase margin even worse. So, cancelling right half plane 0 is very difficult. In the other case, in the LDO case, we were able to convert it to a left half plane, by using that nulling resistor, but in this case is very difficult. So, only way is to just control through your values D, L and your load current. Load current is not in my control, so I can limit it within certain range, and I can define the L. Okay, this is the fixed L you can use, and this is the duty cycle range you can operate, that to ensure that my right half plane 0. So, there is a trade off between bandwidth and your basically range of load current and your duty cycle you can operate with. Okay. So, if somebody wants to cater to very high load current, then you have to limit the duty cycle, otherwise this right half plane 0 will start making problem. Okay. Okay, any questions? Okay, so next class we will cover buck boost, because in order to understand buck boost you have to have the concept of boost. So, now you will understand buck boost in a better way, and what are the issues with there, what are the different control techniques we will talk about, and then we have switch capacitor, DC-DC converters, we will talk about that. Okay.